Hey, hello everyone. So this video, I'm trying to get some intuition about causal invariance, which is an idea that Stephen Wolfram talks a lot about in multi-way hypergraphs. And um, I'm trying to draw it so that I can explore it. And I'm trying to ask the question if a simple rule, like a consensus mechanism, can achieve a outcome that is true irregardless of a sequence of time. That if you choose a simple rule that leads to the same outcome in every case or every exploration of a multi-way hypergraph, that you could that rule could achieve the intended outcome irrelevant to time. So being irrelevant to time is important because if you can do this simple rule in many separate spaces or shards, then you can achieve a different level of scale of transactions in a blockchain system, at least, because you don't have to preserve this sequence of time in states of the system that are not speaking to each other directly. They will need to sync up at some point. So there's going to be some hierarchical rule for which when a state is achieved at a lower, in the lower part of the hierarchy, the lowerarchy, that it's conveyed upwards and across to the other shards, but it's still not dependent upon time. So a multi-way hypergraph, like you can see on screen here, there's actually only two versions despite seeing three. This middle one and these two side ones are the same, but this middle one is different, as you can see the shape. And I'll zoom in shortly. But um, what we're trying to explore is how a evolution within a multi-way system can result in the same outcome. Um, and then how does that affect the network consensus, or like how does that affect the propagation of the um, winning hash or the winning threshold so that all miners reach consensus about the outcome that was achieved, even though one will have achieved it first. And then another question is like, how do we know that that's the definitive one if what you're measuring based off of could be something more fundamental in the same category of the rule? All right, what am I talking about? Let's just zoom in here a little bit. So just in terms of this diagram, I hope everyone can see my screen. It looks like it. Yes. Okay. So this this big mess here is a multi-way hypergraph, and it has um sorry, I should have called this starting rule. Starting rule. Did I do the same thing here? Starting rule. Starting rule because we have different starting conditions, right? So we have starting conditions, which are like initial states. I'm trying to consider these as like minors because I want to see how a miner explores a essentially an irreducible computation space. So they don't know exactly where to go, but it should result in the same outcome no matter what path one takes if the rule demonstrates causal invariance. So the starting rule is BBB goes to A and A goes to BB and C goes to A, and that's in that one. In this one, there's different starting conditions, though the only difference is that this minor A plus over here has C B B B A here, and then all of the same other ones. So this one has one, two, three, four, five, six, seven. And this one has one, two, three, four, five, six, seven, eight. Okay. And then minor A minus is the same as minor A plus in all of these starting rules, the signal it's looking for, and the starting conditions. The signal is just a minimum difficulty threshold. So we're looking for anywhere in this multi-way hypergraph for where the rules converge to a triple B, or actually the rule is three B's or less. So here's a group of B's, but I'm looking for a group of B's that's less than or equal to three. And here's four, and down here is three, but I'll get to why that's a denied result or not a signal. So I guess the so there's I'm trying to say something about it being irrelevant or irrespective of time, but there's still these computational steps. And that in Stephen Wolfram's realm, those steps, those computational steps are computational steps. They're not time. What's the difference? I don't know. But I think when you start to situate things in time, it becomes relative. And if you're trying to speak about time relative to all of these various systems doing an irreducible computation, you're not going to have a global clock. And that's kind of the point. That global clock is the constraining factor on how a system reaches consensus, because it is if there is a global clock, one must order the sequence of transactions based on that clock and being in sync to that clock. The question that was originally posed here was, is there a rule for consensus that is irrespective of time? Which means, does the rule lead to causal invariance between each minor, meaning doesn't matter which pathway they take, it just matters that they're all going to reach the same end rule. And when the space of uh, computation of SHA-256 hashes with all of the typical parameters of like a proof of work blockchain or proof of, I don't know if I can speak about proof of stake yet, but all the parameters, like, you have the transaction set, you hash it, you have the previous block hash, and you have your own nonce, and you're exploring the space running SHA-256, which is an irreducible computation. You're going to be slicing through this massive sea of a multi-way graph. Each miner is going to be like slicing at different angles. It's going to be with different starting conditions, because that's the nature of what one does with a nonce or the bundling of transactions. And so we want to know if you can shard that work of exploring an irreducible computation that is the validity proof that you are not gaming the system. That if you shard that work, you're actually not sharding end state. That state is causally invariant and will be accepted by each node once the acceptable minimum threshold is reached. And I have a consensus mechanism in mind called proof of entropy minima, which establishes an ability to reach instantaneous finality when compared between two nodes, so that it's no longer dependent upon the longest chain. So in a network of nodes, two nodes could reach the minimum threshold and propagate to the network in different gossip protocols, or it could propagate in across the system in and reach different nodes. Like for example, down here, we just take this as a simple global state. You know, like this miner down here, ignore the red and the green for now, but this miner is propagating upwards, and it's going to reach different nodes at different times than one that says starts from up here and propagates down. Um, if we can get a network that sees two chains being the longest chain rule being acceptable, and then moving on to the next step in the process, which is return to doing um, the irreducible computation because we've already reached consensus, or we already have reached the minimum threshold, and it's in our incentive to move on to start mining the next block because the current winning block has already been found. But if a rule exists that says side by side comparison, I heard this one first, and so I accept it simply because it was the longest chain, versus I heard this one first, and then this one comes in. There's nothing that allows them to settle the difference between the longest chain simply because I heard it first, because the sequence of events led to me receiving it that way, even though it could ultimately be the wrong chain, because in the other side of the network, another block was found before I did, and that becomes the longest chain, propagates and reaches me, and then I have to reorient back to the work. The work that I just did is not useful. So, what is the rule that allows for instantaneous finality that two blocks can measure not longest chain, but heaviest chain? And if one uses heaviest chain, it means you're looking at not just the leading number of zeros of a hash, but you're looking at the full hash in binary to see the leading number of zeros, and then comparing that with any other um, proposed hash. And if one is longer in number of zeros, it is a reduction in the space of all possible hashes. Um, it is a entropy reducing signal to have more zeros in the leading set of the hash. And for that reason, it's instantaneously comparable and acceptable. And it's in one's incentive as a node to accept the the heaviest proof, because that is comparable universally across every shard, every node, and therefore you know that's going to get accepted around the network. So it makes no sense for you to maintain the one that you previously heard. Um, I think. And so I'm making this video so I can put it out there. I can start to get feedback, mostly from the from Kwai Carl and Alan and the rest of their team. Um, and for anybody else who knows deeply about consensus mechanisms. And so it was suggested that proof of entropy minima, the consensus that Qua uses, does satisfy causal invariance. And so if we draw it, we're looking at minors, meaning the starting conditions, simplified starting conditions, as they progress through steps of computation, and they run the starting rule, which can be transformed in many different ways, but ultimately does reach a outcome which is globally acceptable, locally determined, globally acceptable. And so that's what will hold the whole network that's sharded in consensus. And then the specific architecture of how that gets propagated up and across to other shards is something else that we can talk about on a different video. But maybe just a quick intuition on how to step through this. So if you start with these initial conditions, you see A, B here, B here, B A here, and you say, take this starting rule, B goes to A and A goes to B, and just start applying that wherever it is the case. And let's take this one in particular. It can make two updates here. Because it's got these two arrows and it says, if you have an A, go to BB. So here's an A and here's an A. So it's going to have two rules that update, and it's going to take this middle A, transform it to BB, and put it all back together and give us AB, BB, and the last B. A, B, 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 and the last B, A, B, B, and the last B. So these blues are the resulting transformation. Here's the transformation layer, and here's the resulting state. And here's where A, B takes the first A, transforms it into BB, and so you get BB, BAB. And that arrow goes all the way here, BB, which other transformation rules also get to it. And if you do that at every step and you're looking for a particular signal, like 3Bs or less as your threshold, you can see how there's no agreed upon outcome from any of the pathways taken through this multi-way hypergraph until you come down here and you find signal. This is the detection. This satisfies the minimum difficulty threshold, and it puts out this signal, and it's in irregardless of all the other nodes in the system, this is a potential winner. And so it will put it out there. And despite meeting the minimum threshold, it will get compared to what all others have heard and will be measured based upon the entire number of zeros in the binary field of the entire hash. And that brings us down to how the network decides if that is a satisfying signal or not. No, it's not how, it's just about if. So the network on the left in green accepts the result of minor B here. Accept result, move to block n+1 because we're in block n, and we go to the next one because even though this one with which started at different starting conditions, but runs, uh, did this same rule have a C go to A? I'll have to check with my team if that's okay or not. I would prefer not to have an extra rule. I don't know why I put that in there. Maybe it was because to see what happens if the space of the C gets explored. Well, anyway, uh, the point I'm trying to demonstrate is that down here at step 9, minor B finds the signal. Down here at step 9 for minor A plus, it has not yet reached the minimum threshold. Step 9, nothing. Step 10, still nothing. These are not signals. So, but at that same time where it's at step 10, about to do step 11, before it gets down here to step 12, where it will meet the minimum threshold, um, at step 9, I should move this up a little. I want to say at step, I mean, it's not going to immediately propagate, right? But at step 9, where this one is found, this work, which this is a demonstration of it being propagated, this work is no longer important. There's no more point of doing this work because there was already the signals found, and so the incentive of minor A plus is to accept the result and move to block N plus one, which means go back to starting condition one, take the block hash provided by minor B over here, go into the mempool, take the set of transactions, bundle them up, um, and then run the nonce through and iterate across SHA-256 until they try this whole results again, and hopefully they win, and it's in their incentive to. Over here, if this miner does not um, accept that this was a signal of greater of heaviest chain based on the amount of leading binary zeros, leading zeros in the binary field of this total hash, then this one is either doing um, is is wasting work. Step 9 here is either wasting work or it has denied the result because it has a deeper, a heavier um, block to propose. But it's not in its incentive to deny this signal simply because it heard a signal somewhere else in the network and was running the longest chain rule. So between this scenario, miner B won the most recent block, and it will revert back to running the next set of hashes based on this signal it found. And so will miner A plus, which will be in competition at the greatest amount of um, exploration of this space of hashes. And this one will be at a disadvantage because it will not have accepted that result. So, um, that's my initial kind of intuition of trying to understand computation, causal invariance in a blockchain system. And I'm starting to write that up this is kind of a free flowing prompt, but I'm trying to get the intuition about how one thinks about causal invariance, and um, you need a little bit of intuition about Wolfram, at least in my perspective, to really get it to sink in. But um, down here, what's it like to walk through a multi-way hypergraph is what I just showed in the previous example. And here's a simple example of a multi-way system with that has a rule and has updating events. But when we combine a multi-way system and a hypergraph can join uh, an edge to any number of vertices. And when we think about hypergraphs and the updating rules, we can start to get many dimensions. And I shouldn't be going here because this is more about Wolfram physics than it is about blockchains. But it helps with getting the intuition about causal invariance because it's a directed. Okay, yeah, okay. So here's the point. The point is, how does one optimally navigate a multi-way hypergraph so that so that the network is not doing more work than it needs to and doing wasted work or increasing entropy is like increasing noise in the system. What you want to find in the space of exploration of a multi-way hypergraph that, practically speaking, SHA-256 gives us is a rule that is most succinctly navigates the space and does so with with a particular feature that the end result will be causally invariant. It will be A, despite starting with many different initial conditions and many different ways of transforming the rule throughout computational steps. And this, um, to get to this result means that you don't need a global clock to order the events. You just need to compare which hash has greater amount of work done in it by comparing the whole hash, meaning comparing the whole space of possibilities and electing the one that proves it has reduced entropy. um, I'm going to stop there because I think I've broken something internally, but I'm going to put this on Twitter and see if I can get any feedback or discussion on it. Thanks for watching.